Okay, I'd like to look at the 3.2 quick check about solubility. So the first thing here, we have a nice picture, and this is kind of showing that, if we add different ions together, we're going to get precipitates. And it's this whole idea about precipitate breaking up and going back together that is the essential portion of this kind of equilibrium. So for the solubility product, can we write the KSP, the equation for the KSP of Ag2CO3? And what we're talking about is, what we're really saying is that if I had some silver carbonate, and that would be a solid, that would break up into two Ag pluses, aqueous, and a CO3 2 minus, aqueous. So that's the chemical equation that's associated with this. So the next thing says, okay, we have the value of the solubility product constant is 8.1 times 10 to minus 12. Calculate the value of the silver ion in 100 milliliter of a saturated solution. Well, it doesn't matter what the volume is of the solution. If we're just getting the concentration, it can be of any size solution. Any saturated solution of silver carbonate will have the same concentration of silver. So the volume is just an extra piece of information we don't need. The 25 degrees, we're not going to use that either. It just means that this value is valid at 25 degrees. Since we have a solution, we can see it's a 1 to 2 reaction, then if we define solubility as S, then we're going to see what happens is that I'm going to have a 2S of silver ions, and I'm going to have S of carbonate ions. When I put it back into my KSP expression, which is the concentration of Ag plus squared times the concentration of CO3 2 minus, then I'm going to get 2S squared and S, so that's going to come out to be 4, 2 times 2 is 4, S squared times S is S cubed. So the KSP is 4S cubed. So knowing that my KSP is 8.1 times 10 to the negative 12, then I can calculate that my value of S, all I have to do is divide by 4, and then I have to take the cube root of this. So when I do all that, I find out that S equals 1.265, so I'm going to say 1.265 times 10 to the negative 4. Okay, that's my solubility. So that's the best concentration of silver carbonate I could make. But I know that my silver is going to be 2S, so the actual answer for this reaction is going to be 2S, which is 2.5 times 10 to the negative 4 molar. So that's my answer, the silver ion concentration. Okay, the next question is talking about comparing 3 different compounds. Now, these 3 compounds, we can't just look at the KSPs and say, okay, a large KSP is soluble, and a small KSP is not very soluble, because they're not the same kind of compounds. We can see the first one here, that is a 1 to 2 compound. This is a 1 to 1 compound, aluminum and phosphate, and this is a 1 to 4 compound. So first off, we have to say, what's the relationship between solubility and KSP? So from the pattern we've seen, we can see that the KSP here is going to be, okay, lead, we're going to have S, and chloride, we're going to have 2S, but when we put it into the expression, the KSP expression is going to be squared, so this is KSP equals 4S cubed. In the same way, the second one is going to be S times S, so KSP equals S squared for a 1 to 1 compound. And our last one, we can see that is going to be S times 4S, because the hydroxide would be 4, and it's going to be to the 4th power, and that comes out to be 256 times S to the 5th power. So now I'm going to use my KSPs, calculate numbers for S's in each case, and then compare the S's, because the larger the S, the more soluble it is. So I want to go from the smallest value of S to my largest value of S to get my answer. So I'm going to take a moment and calculate. Okay, doing my calculations, I get these 3 values, and I had to take the cube root and the square root and the fifth root and divide by numbers. And so I can see out of these, my smallest one, that the aluminum phosphate, this is my least soluble. And the lead chloride, that's the most soluble. And this other one, this is going to be middle, those other two. Okay, the last part here is you want to do a precipitation. And if we're talking about lead chloride, okay, and there's a lot of different chemicals in here. You got to view what is the KSP. So we're talking about the KSP of lead chloride. So we're talking about PbCl2 solid, and that's going to be breaking up into Pb2 plus and 2Cl minuses. The KSP is concentration of lead ions times concentration of chloride ions squared. So we're going to get these two concentrations, substitute them in, and calculate our QSP and decide whether a precipitate forms. So doing these calculations kind of quickly, my lead ion I have to start with 0.02 molar, but I take into account the fact that I'm mixing two solutions, so 75 over a total of 100, so my lead concentration is going to be 0.015 molar. In the same way with my chloride concentration, I have 0.01 molar, but I have 25 milliliters out of a total of 100 milliliters. So the number I'm going to use here is 0.0025 molar, and that's going to be squared. So when I do all of this together, so when I do my calculation, I get 9.4 times 10 to the negative 8, which is much smaller than my KSP of 1.7 to 10 to minus 5. So there's going to be no precipitate.